There are many applications that involve a circle spinning. Let's say that it is a gear that's turning, or maybe we're looking at a satellite orbiting around the Earth, or anything that forms some sort of circular path. And oftentimes we're interested in knowing how fast it's moving. So how fast is the gear spinning? How fast is the satellite rotating around the Earth, or revolving around the Earth rather? And so we'd like to take a look at two types of speed when it comes to rotation, referred to as linear speed and angular speed. We'd like to start by looking at linear speed, which typically, if we think about linear speed, we might think about traveling along a straight road. So here we've got our fancy sports car that we're trying to determine how fast this car is moving. So we have to first of all recognize that over a certain distance, okay, which we'll refer to as D, that it took a certain amount of time for this car to get to a certain location, okay? So let's say that, that we look at the distance traveled and realize that if I look at distance might be in feet, for instance. And I know as well that if I were to take a look at the rate at which this is moving, okay, that's a certain speed. So the speed would be referred to as R, or the rate. And of course, the time that it takes to travel that distance is referred to as time. So you should remember the formula that says that distance is equal to rate times time. But I'd like to demonstrate why that works. I mean, if we just think about it in terms of units, it works as well. The units for rate might be something like miles per hour or feet per second. So let's think about this. If this is feet per second, the only way for the feet on the left to equal the same units on the right is if I multiply the seconds to cancel out the denominator. And sure enough, you can see why now that distance is equal to rate times time. So to take this a step further, let's say that we wanted to solve for the rate, which is the speed. So let's say we looked at the speed in a slightly different way. And we thought about the speed as velocity. Now, speed and velocity are not the same, because velocity is actually the speed and a given direction that you're moving. So if I happen to be moving in one direction, the velocity would be positive. But if I was moving backwards, the velocity would then be negative. So we're going to start to look at this in terms of velocity, where we recognize that velocity is speed with a direction. Okay. And so what that implies then is that I could rewrite distance equals rate times time as distance equals velocity times time, which also implies that if I want to solve for the velocity or the speed, I simply divide by time, which also makes sense because if I take the distance traveled divided by the time that it takes to travel, then I get something like feet per second, which makes sense that it's velocity. So we'd like to look at this in another way now to recognize that if I were to look at this circle now we're looking at this from a different perspective because the distance that we're traveling is now going to be along the outside of a circle. So now picture a point that's on the circle that's now going to start rotating around at a certain speed. And what we're trying to do is determine what is the linear speed. Now it seems a little peculiar. We maybe should have called this circular speed, but linear speed is basically saying if I were to take this circle, think of it as a string, and pluck it apart and pull it out straight like this straight road, then that means that S is similar to D. So we could recognize in this situation that the distance is actually equal to the arc length. And remember that the arc length is S. So it should make sense then that the angular, the linear speed, okay, and we'll refer to this now as linear speed. Should make sense that the linear speed then, which we will call v, is simply equal to the distance traveled over time, but the distance traveled now is s. So that means that the velocity is equal to s over t, and this is the formula we'll use for linear speed. Now there is another type of speed when it comes to rotation as well, and we refer to that as angular speed. And so there's a pretty logical way to think about this as well. So let's say that as a gear is turning, okay, or as a wheel on a car is turning, not only is the arc length changing, but as the arc length changes, the theta changes as well. And the rate at which the angle changes as you move around this circle, how fast is that circle or that angle changing? So if it was changing really slowly, maybe like the gear on a watch, it would be relatively slow. Pi over 3 radians per second. But maybe it's a tire that's moving on the freeway and now it's going really, really fast. And so maybe it's going 18 pi radians every second. And so what we should recognize then is that angular speed can be thought of in terms of the units of radians per second. And so notice that radians is measured as theta and seconds is represented as t. So we refer to the angular speed as the Greek letter omega is equal to the angle over time. And therefore, this is the formula for angular speed. So since speed or velocity is always going to be some amount of distance or radians per time, that's why we're dividing by time. Now there are a couple of other ways that we could actually represent this. So let's go ahead and take a look at a couple of other representations of these formulas before we get started on an example. Oftentimes we're given different information within an application problem. So if I wanted to find the linear speed, sometimes I don't know what the arc length is. So oftentimes we can think back to what the formula for arc length is and realize that arc length, S, is equal to R times theta. So we could actually rewrite velocity here as R theta over T. At which point now, if I'm given the radius of the gear and maybe the angle at which it turns through, now I can use this formula instead. But now by putting it into this form, we should notice something else as well, that I could basically take out the V or the R value from that fraction and rewrite this as V equals R times theta over T. But notice what theta over T stands for. Theta over T is the angular speed. So if I want to find the linear speed and I'm already given the angular speed, then I could just simply find R times omega. So each of these formulas here are going to be interchangeable, and it all depends on what we're given in terms of how we're going to solve for the particular application. So let's take a look at an example. On a belt that's being turned to rotate a pulley here. And in this particular situation, it says that a belt runs a pulley where the radius is 6 centimeters at 80 revolutions per minute. So we should think about what that actually means. It means that from from some starting point, when I start my stopwatch, it's going to make a full rotation and then 80 more of those rotations in 1 minute. So notice that this doesn't represent any sort of speed at this point, but let's just go ahead and write out the things that we are given. We're given, first of all, that r is 6 centimeters. And we are given something about this 80 revolutions per minute. So that is some sort of speed, except for the fact that it's not angular speed and it's not linear speed, because linear speed would be in terms of a length over time, and angular speed would be in terms of a radian measurement over time. So the first thing that we're going to have to do is convert that revolutions per minute into angular speed. Let's think about how we can do that. So if I have 1 revolution, I should recognize that 1 revolution is equivalent to 2 pi radians. So if I want to convert from revolutions per minute into radians per minute, all I'm going to need to do to find my omega, or my angular speed, well, before we find that, is find out what my radians per minute are, which is essentially what I'm doing here. So my radians per minute is going to be 80 revolutions per minute. Maybe I'll write it as revolutions per 1 minute. And then we can multiply by 2 pi radians over 1 revolution. And the benefit of doing that, obviously, is to cancel the revolutions, and all that's left is my radians per minute. So in this particular case, I find out that my angular speed is 160 pi radians per minute. Which makes sense if every radian, or if every revolution is 2 pi radians, okay? But now we want to find our linear speed. Now, notice that there were a few different formulas for this, okay? So taking a look back to our formulas, I could use this one, but I'm not told how long it took to make a revolution. I'm not told anything about the arc length. All I'm given is the radius and the angular speed. So it should make sense that in order to find the linear speed, I should use the formula that says r times omega. So in this case, I could see that v, velocity, is equal to my radius of 6 centimeters times, and let me write out the units here, 6 centimeters times 160 pi radians per 1 minute. Now, I wanted to write it out in this way so you can really see something interesting here. When I multiply 6 times 160, okay, then what I can do at this point is find and just multiply this out, which gives me 960. So my velocity is 960. But now look at our units. I know I have centimeters in the numerator, and it looks like I'm multiplying by radians in the numerator per minute. Okay. But notice radians, remember, are unitless, because a radian measurement is nothing more than the arc length divided by the radius. And so there is no unit for radians, so I didn't technically even have to write radians in my numerator, which is why my final result is just centimeters per minute. Now, I'm not quite done because of the fact that I'm going to have to work through this to get the correct units that it asked for. So in this particular case over here, it asked me for radians per second, and it asked me in the second one for centimeters per second. So I'm going to have to go through one more step here. We know that there are always 60 seconds in a minute, so if I want to change this, then I have to cancel the minutes, which means I should put those in the numerator. And therefore the seconds in the denominator. 1 minute is equivalent to 60 seconds. So now I can see that my angular speed is 160 pi over 60 radians per second, which when I simplify gives me an angular speed of 8 pi over 3 radians per second. So anytime it's always important in an application problem to know what units you're using. So pay attention to those units, and this right here is my final answer. But for my linear speed, it's the same idea. I've got to multiply by 1 minute over 60 seconds in order to cancel the minutes, which means I'm really doing the same thing again. I'm simply taking my velocity is equal to 960 over 60 centimeters per second. And now when I divide, that ends up giving me 16 pi. I'm sorry, that was 960. I forgot something up top here, which was really important. Shame on me for doing that. There was an extra pi here. So notice that this should have actually been 960 pi centimeters per minute, which means that it's actually 960 pi over 60. Okay, so that final result gives me 16 pi centimeters per second. Now we could leave it as is if we choose to. If we want to, come up with an an approximation, we could say it's approximately, we could do the calculator work, pi times 16, right? So it's approximately 50. Okay, so we could say it's approximately 50 centimeters per second. But leaving quantities in exact form is perfectly acceptable. Let's look at another interesting problem that refers to a satellite tracking around or orbiting around the Earth. It says that a satellite traveling in a circular orbit is approximately 1,600 kilometers above the Earth's surface. And it also tells us that the radius of the Earth is 6,400 kilometers. So because the satellite is technically revolving around the center of the Earth, then what we really need is this distance right here, which is the radius of rotation. So we're going to start off by just recognizing that the radius is equal to 8,000 kilometers. And part A is asking us for the to approximate the linear speed of the satellite in kilometers per hour, right? So one thing that's important about this is that it takes 2 hours to make an orbit. So I'm thinking of a couple of different ways to approach this problem. We could figure out the arc length for one orbit. We could find out maybe the angular speed. There's lots of ways we could go about doing this. So let's just start off with maybe recognizing that if I wanted to determine the angular speed, then I need to have a certain number of radians per hour, right? And so I can see, first of all, that one orbit, okay, is the same as 2 pi radians. And I also know that I could, or rather, maybe I should rewrite this in another way. I should recognize that it's 2 pi radians is equal to 1 orbit. And I'll explain why I flipped this fraction, okay? But what I wanted to do here is I want to cancel out the orbit, and I want to have radians on top because I need to have radians per hour. Okay, so if that's the case, then I need radians to be on top. I need hours to be on bottom, which means I need to cancel orbits. So this is just a conversion factor again that will allow me to cancel. But in the problem, it said 1 orbit is actually 2 hours. So that means that omega, or my angular speed, is equal to pi radians per hour. Well, remember as well that because I have my angular speed, I could find my linear speed by simply taking my radius times omega. So that's 8,000 kilometers 8,000 times pi radians per hour. And since radians are unitless, that tells me that my linear speed is going to be 8,000 pi kilometers per hour. So that's one way that we're able to figure out our linear speed. We just have to figure out how am I going to find the information that I need in my formula. Okay, and we force ourselves to use the information given. Or we could have done this maybe a slightly different way. We could have started by saying, well, let's find the arc length for one orbit. Okay. Well, I know that S is equal to R theta, which is equal to 8,000 times 2 pi, which means that my arc length is equal to 16,000 pi kilometers. Well, my other formula for linear speed is V equals S over T. So because S is 16,000 pi kilometers, and I know that one orbit takes me 2 hours to complete, then that must mean as well that my linear speed is 16,000 divided by 2, or again, 8,000 pi kilometers per hour. So in a lot of problems, it just depends on what you see or what you recognize you're able to do in order to fit the formula that you want, okay? So that takes care of the linear speed. But I want to calculate the distance that the satellite travels in 4.5 hours. So I can think about this kind of logically. I know that it's going to take 2 hours to travel one rotation. It'll take another 2 hours to do another rotation, so that's already 4 hours. And then one more half an hour would take me up to here because a full rotation would be 2 hours. So that's one thing to kind of recognize about what's going to happen with our time of 4.5 hours. Well, let's think about what we're given. We're given a time, we're given a radius, we know a velocity. So what we're really trying to find is the distance traveled, which is an arc length. So the distance is going to be a slightly different problem here, because in order to find distance, I need to use the things that I know. I know that there's a formula that involves distance, which is S. I'm trying to find S. So why don't we write this as velocity is equal to S over T, which allows me to rewrite my S as S equals velocity times time. But notice this shouldn't be too surprising, because isn't that just distance equals rate times time? So if I want to find the distance traveled in a circular orbit, I just need to take my V and find that V is 8,000 pi kilometers per hour times the number of hours that I'm traveling, which is 4.5 hours. And notice that that's canceling my hours, which gives me that my distance traveled is going to be 36,000 pi kilometers. So again, just as every application, every problem is different, but what's most important is to recognize which variable am I trying to solve for, and how can I use the information that I have to fill in the formula that I'm going to need. And so when we're trying to find anything related to speed and rotation, we know that we're using these formulas from this lesson.